Welcome to the Alpha Training and Consulting's online training program. Today's module is entitled Statistical Methods in Reliability Engineering, from Theory to Practice. Now this is going to be a rather short module, so it's just an introduction to statistical methods. Reliability engineering is very much mathematically oriented. And in the ASQ CRE is probably one of the most analytical of all ASQ's certification exam. It demands more math, more knowledge of math, etc. And it's one of the reasons it's one of the most failed exams that ASQ offers. So there's a lot of math. We're not going to come close to covering all of it, but we'll introduce you to it. Statistical methods form the backbone of reliability engineering analysis. Notice the word engineering in there. For ASQ CRE candidates, ASQ, American Society for Quality, Certified Reliability Engineering candidates, understanding these techniques is crucial for interpreting failure data, making predictions, and supporting engineering decisions. The first thing you need to know is the exponential distribution. So this is probability distributions and reliability. This is one. It's a pretty user-friendly one. It's not difficult to use at all. The exponential distribution is fundamental in reliability engineering, particularly for modeling the time between failures when the failure rate is constant. So you have decreasing failure rate over time, constant failure rate, and increasing failure rate over time. This is in that constant failure rate portion where you use the exponential distribution. And here it is. This is the one most commonly used, the bottom one there. Reliability of given time equals base log E to the power of negative failure rate times time. Now, the mean time between failure is the inverse of failure rate. So you could also create an equation that says reliability of a given time equals base log E to the power of negative time divided by mean time between failure would be a correct formula also. This is a very common formula. Remember, this is for constant failure rate only. Then we have the Weibull distribution. The Weibull distribution is versatile and can model increasing, decreasing, and constant failure rates, making it extremely useful in reliability analysis. So this is a very important distribution. It's not as user-friendly. Okay, this is the formula for failure, probability of failure at a given time. Beta is the shape parameter, nu is the scale parameter. And by manipulating all those, you can model decreasing failure rate over time, constant failure rate over time, and increasing failure rate over time. It's a very powerful formula, but not nearly as user-friendly. Look at that formula versus this one, okay? And so oftentimes when we're at that constant failure rate, we like to use this equation here versus the more difficult one here. But it is a very important distribution. The other one is the normal distribution. The normal distribution is important for modeling wear-out section of the bathtub curve. So decreasing failure rate over time, constant failure rate, increasing failure rate. This increasing failure rate over here is where we use the normal distribution. And its formula is very simple. Mean time between failure minus a given point in time of question divided by sigma. You look it up in the Z table, and that way you can get your reliability for a given period of time during that wear-out period. All right, another important part of reliability engineering is life data analysis, censored data. That's a very important term, so let's talk about that. In reliability testing, we often encountered censored data where we don't observe the actual failure time for all units. Some of them fail, some don't. Then that would be considered censored data. Understanding how to handle censored data is crucial. Write censored data, test ends before all the units fail. Well, how do you take all that into account? Well, we teach you how to do that. Right left censored data, failure occurred before observations began. Okay. Interval censoring, failure occurred within a known time interval. So that's all part of reliability engineering. You have to learn how to deal with right censored data, left censored data, and interval censoring. Another important term, MLE, maximum likelihood estimation. MLE is a powerful method for estimating distribution parameters from live data, especially when dealing with censored observations. It provides the most likely values of parameters given the observed data. You're dealing with probability statistics because you can't say exactly this is what it's going to be, so you give confidence intervals. Okay, hypothesis testing and reliability. Reliability demonstration testing. Hypothesis testing helps determine if a product meets reliability requirements. Okay, and you have null hypotheses and alternative hypotheses. And you use tests like the t-test, the z-test, the ANOVA test. The chi-squared test is an important one sometimes in reliability engineering. So we use all kinds of tests. We use parametric tests, non-parametric tests. They're all part of the ASQ CRE body of knowledge, and it's important that a reliability engineer is very confident at using these hypothesis studies. What does a hypothesis study tell you? Did something change? Did the reliability change with this design change? You know, those are very important types of questions that you'll need to answer. Chi-squared goodness of fit, used to test whether observed failure data follows a particular distribution. This is essential for validating distribution assumptions and reliability models. And if you know, hey, this is a normal distribution, that's good to know. Why? Because you know it's in the most likely in increasing failure rate over time, this part that you're analyzing. And if it's exponential, you know it's probably in the constant failure rate period of time. So this can be a very powerful tool for reliability engineers. Confidence intervals, I've already talked about those, but let's do it again. Confidence intervals provide a range of plausible values for reliability parameters, accounting for uncertainty in estimates. So you say, I think it's going to last 1,000 hours before it fails. But 95% of the time it'll be between 800 and 1,200. That's somewhere in there, 95% of the time this is going to fail. So you don't usually have a point estimate, you have confidence intervals. Reliability confidence bounds. For exponential distribution with constant failure rate, the confidence bounds for reliability can be calculated using the chi-squared distribution. All right, regression analysis is also something we use. Accelerated life testing. Regression analysis is used to model the relationship between stress factors and failure times in accelerated testing. Arrhenius model for temperature acceleration, power law model for mechanical stress, Eyring model for multiple stress factors. So we use regression analysis especially in accelerated life testing. But it's not the only thing we use it in. It's a very commonly used tool in reliability engineering. Practical applications. Here's an example problem, Weibull analysis. A manufacturer tests 1,000 components and observes the following: 20 failures by 1,000 hours, test terminated at 2,000 hours, 80 units survived. So it is censored data because not all of them failed. Using the Weibull analysis with MLE, we can estimate the shape and scale parameters to predict future reliability performance. So there's a practical example. Software tools. The ASQ CRE exam doesn't require specific software knowledge, so this isn't about the test. Familiarity with these tools enhances practical applications. These are some of the softwares that they're pretty common. Minitab for statistical analysis, pretty common. Reliasoft Weibull++ for life data analysis. You may use R for advanced statistical modeling, or Excel for basic calculations and plotting. So there's many different softwares out there. That's just some of them. Trust me, there's many more. Conclusion: statistical methods are the foundation of quantitative reliability engineering. Mastering these techniques enables you to extract meaningful insights from failure data, like the example problem we just showed you. Make informed decisions and communicate results with confidence. Continue practicing with real data sets and consider our comprehensive training program for hands-on experience with these methods. Next steps: mastering reliability engineering fundamentals is just the beginning. Continue your ASQ CRE preparation by diving deeper into statistical methods, design techniques, and testing procedures. Our comprehensive training program covers all these areas in detail. Our class is 124 hours is the estimated time that it takes to prepare for the ASQ CRE exam. We have approximately 90 lectures, as at least at the time of this publication. The cost of this class includes shipping for the instructor notes, the ASQ CRE handbook, and a calculator. So you don't really need to buy anything. You purchase our class, you get everything you need. I look forward to joining you on your ASQ certification journey. I hope you choose Alpha to help you prepare. The class also comes with 4 mock certification exams, which really helps you in your final preparation steps. All right, you can learn more about my class by going to www.alphatc.com. Scroll down till you find the CRE class. Click on that, and it'll show you all the lectures. It's totally transparent. There's a video there you can listen to. I also have a website just for this class, and it's found at www.asqcre.com. If you have any questions, just contact me at my email address there, john.lee@alphatc.com, and I'd be happy to answer any questions that you may have. We prepare for many different ASQ certifications. As you see there, we have a lot of classes, so keep us in mind for all of your ASQ certification preparation needs. All right, thank you for joining me in this lecture. I hope you learned something new that will hopefully clear your mind about what reliability engineering is all about, and hopefully you'll consider our class. Thank you, and have a great day. Goodbye.